Hello, student and audience. Title of this lecture is rather long. Small signal model-based analysis of frequency response of converter power stage. So it has a long name. We went through 4 lectures, and most of them we discussed the structure of offline converter and the power stage operation of flyback topology, and some bias circuit and the compensation structure of feedback circuit composed of optocoupler and operational transconductance amplifier. Those stories are kind of steady state circuit analysis, okay? But the remaining part, we need goes to some dynamics and control of this flyback converter. So I thought it's good to review some basic highlighting summary of small signal model and frequency response of PWM converter in comparison with those of linear time invariant circuit. Okay, and the discussions will be very general for the most student and audience who are not fully exposed this kind of story, dynamic and control of PWM converter, and some of students are not taking this course in series, and some of audience, I think most of audience are not watching this video in series. Okay, so I'll present some basic idea about this small signal modeling and frequency response of PWM converter, and that will be the fundamental background for the forthcoming lectures about the dynamic analysis and control design of offline flyback converter. So this can be considered as a review course or entertaining course for the most people. But I thought this will be necessary. Okay, so let's review the basic definition or implication of this frequency response. First, consider the frequency response of linear time invariant system. Suppose we have linear time invariant system here, maybe some linear circuit. This is the input and this is the output, and you are applying the sinusoidal waveform in the input of linear time invariance system. Then output will be sinusoid, and the frequency and the shape remain the same. 2 things will be changed. One is amplitude, another one is phase delay. So for one particular frequency, the change in the phase and the change in the magnitude or amplitude of this sinusoidal signal is defined as amplitude response and phase response. Okay, but what we really want to do is to evaluate this kind of story for the continuous frequency range for the given range. That is defined as the frequency response of linear time invariant system. And frequency response of linear time invariant system contains all the information, static or dynamic information about the system, and one particular most important outcome is transfer function of input to output variable, which can be used to evaluate the stability and the dynamic performance of the system. Okay, somehow we want to extend this concept to the PWM converter. So PWM converter is nonlinear and time-varying system. So it is not easy. It is not suitable to directly apply to those concept of frequency response concept. Okay, so the method we have taken is this one. So this is the PWM converter, open operation PWM converter, and this is the power stage, whatever power stage will be here, and this is the PWM modulator, and this is the unit gain buffer, and this is the DC voltage, which is divided by 2 resistors, and there is some DC value here. defined as V cone. Okay, and you apply the AC sinusoidal waveform, then this capacitor is large, more than 0.1 microfarad. So most likely it works as a short circuit for this signal. So signal will be sitting on top of this DC value, and that signal is passed through this unique gain buffer, and it appears here. Okay, then this will modulate this pulse generate the pulse width modulated switch drive signal, and that will generate the out voltage, which consists of DC here, and it is reasonable to predict there is a sinusoidal variation here, this red curve, which is generated by this excitation. Okay, that is reasonable. Okay, so suppose this red curve is sinusoidal with the same frequency, which is much lower than this switching frequency. Okay, so this is the sum of DC component and this low frequency sinusoidal component and the high frequency switching ripple component, which is this. Okay, so then we can consider this is as the input to this system, and this red curve is output of the system, and you watch the phase delay between them and the difference in magnitude of this one, then you can define something very similar to the frequency of linear time invariant system, which is adapted to this PWM converter. Okay, that is the basic idea of frequency response of converter power stage. Okay, so for the linear time invariant system case, so consider this is the input, sinusoidal input, and this is the sinusoidal output. Okay, let me move this one down here. Okay, then for the linear time invariant system, maybe there is a fixed slope here. Then you excite this signal with sinusoidal input, then output will be sinusoidal, determined by slope of this curve. Okay, this is not 100% accurate analogy, but this is very useful to understand nature of this. Okay, so for this, if you change the operating point, this slope remains the same. Okay, that means frequency response remains the same. You increase the magnitude of this one, then magnitude of output will be increased in proportion to the increase in the input. Okay, so everything remains same. So we have the proportionality property. Okay, if you change the frequency of this signal, then you will have another line segment like this. Okay, so once you change the frequency of excitation, maybe you have new curve here, then this curve will be linear. Okay, so this is the concept of the linear time invariant system and the sinusoidal response. Okay, let's consider the PWM converter case. So I don't know what this is. There is something like this. This is Vs and Vo of this PWM converter, maybe voltage gain or something. Okay, some details. Okay, something like this. This is non-linear. All right. So the operating point is here. Then you excite this with small sinusoidal waveforms. Then output will be something similar to this. Then when this magnitude of the sinusoidal component is sufficiently small, you can replace this with this line segment, and you can consider this tangential line segment as linearized line segment, locally linearized gain of this nonlinear curve. Okay, the difference between this one and this one is if you change the operating point, quiescent point, then this one will be different. If you increase the magnitude of this, then you will get something else, something different from this. There is no proportionality characteristic here. So that is the problem of PWM converter. So for the PWM converter, we accept this response. Okay. Same with something very similar to get something similar to this, we need two approximations or two procedures. One is elimination of a ripple component that is done by the averaging process, and the other one is we just localize the dynamics of this one in the very close vicinity of the operating point. Okay, you are staying only around this. Don't go outside. Don't go too far from this operating point. Then you will have something very similar to this. Okay, that is the basic assumption, and that is the basic limitation of this story. Okay, so PWM converter, we extend this idea. So frequency response of PWM converter requires the averaging and local linearization process. But if you stay in the close vicinity of the operating point, you will get something very similar to the transfer function of this linear time invariant system. Then you can apply, you can adapt to the older your existing knowledge about the linear time invariant system, like transfer function, Nyquist, root locus, everything. Okay, feedback theory, everything. So that is the prime purpose of developing small signal model of PWM converter. If you have small signal model, the model embraces all your knowledge about the linear time invariant system to analyze the dynamics, stability, everything about your PWM converter only locally. Okay, on the assumption that you are not changing, moving, not widely from the given operating point. That is the requirement. Okay, so with that assumption, this diagram makes sense. Okay, if there is a sinusoidal perturbation coming here, we will generate this. Okay, so this is the perturbation in control voltage. Okay, and if you add perturbation here, there is perturbation in input voltage. So input voltage now is DC plus AC. Then you extract this AC component. This is the perturbation, the load current, which represents perturbation in this resistance, load resistance. Okay, then you get the similar things. Okay, from this definition, you have three transfer functions and three corresponding frequency responses of converter power stage. So this is the control to output frequency response. This is the input to output frequency response, and this load current to output frequency response. Okay, this is the basic background for the small signal model and transfer function and the dynamics and dynamic analysis and control design using the techniques only applicable in the past linear time invariant system. So we are extending that concept with this assumption. Okay, so this is the basic idea of this analysis, frequency response analysis. And basically there are two approaches. One is empirical approach, and another one is analytical approach. Okay, so we discussed the empirical approach first, but our main interest lies on the analytical approach. That is related with the title of this lecture. So small signal model based analysis of frequency response of converter power stage. You can do the same thing without this small signal model based on the empirical approach, but we are not interested in that. That is also very useful, but the topic here is analytical approach based on the small signal model. Okay, so two empirical methods. One is the using the hardware equipment, measurement equipment. So this is simply the measurement using impedance, using the instrument called an impedance analyzer, and the other one is simulation. Okay, simulation using circuit simulator All right, you can read this, you can read this, okay. We discussed this several times, okay. I don't want to repeat them, all right. But the software, the PCM is providing the automatic procedure of this computational method, okay. And simplest is another one. So this one is cheap and handy, okay. This one is expensive and not user friendly, okay. So I decided to use this. Prime reason for that is there is a free copy, license free copy available for anybody. That is the prime reason. Let me explain the concept of empirical evaluation of, for example, control to output transfer function. So this is the hardware. It's not the hardware. This is a drawing, but assume this is hardware. Okay. So you have converter. This is the setup for the open loop frequency. So you inject this signal onto the to DC. So this is the control signal. V-con is DC component, AC component, and that composite control signal is compared with this fixed length signal, and the VQ is generated here. This is the pulse width modulate switch drive signal. Okay, so this is then with this setup you can use this instrument and experiment or measurement. Okay, and you copy same thing with this PCM model. So thing here is the model. This is the same as this. Okay, this is the I call it switch model, which is just a circuit implementation of this hardware. So result of this and result of this should be the same. Okay, so this is the experimental result. You generate some result, and this simulation using this laptop computer will generate the plot, and the two plots should be the same. Okay, and the very critical concept is continuous duty ratio DT. Why this one is so important is obvious. Okay, in the PWM converter, most of the signals are continuous analog signal. Okay, this continuous signal, there is only one discrete or digital or discrete time signal. That is the switch driver signal. Okay, so they are not comparable each other. So we need some link between this analog signal and the digital signal. For that purpose, we developed this concept of continuous duty ratio DT. Okay, so this is the explanation about that. Let me explain this first. Right? Okay, so this is the pulse width modulate switch drive the signal VQT. Okay, so this is the generation of that signal. So we are comparing ramp with this sinusoidal waveform on the top of this DC value, and we evaluate duty ratio. Forget about this first one. First one is unnecessary or confusing. How I do this? I need to get this wide one. Okay, then delete this. Forget about this. This is the switch drive signal. You wait one switching period, DTS, and end of this switching period, you calculate this the duty ratio and put one dot here. Okay, and if the next switching period, you wait one period, and at the end of this period, put another dot here. Okay, then you continue doing this. Okay, then depending on this length, that dot will be trace out this sinusoidal waveform, very similar to this one. Okay, and you connect this one, and you assume this switching frequency is sufficiently high, then you will get continuous curve, something like this, and this can be considered as the continuous duty ratio DT. Okay, this is the only story. Just conceptual explanation about continuous duty ratio dt. We have strict mathematical definition of dt. I'll discuss that later, but I think this one is easy to understand and more understandable for every student and for every audience. Okay. Then you have this sinusoidal component, and we have DC component. DC component is steady state duty as D, and this time varying component, this red curve, red arrow, double-sided arrow is DT hat, which is small signal continuous duty ratio. So this DT is continuous duty ratio. This is the combination, sum of steady state duty ratio and this small signal continuous duty ratio D hat. Okay, this is the AC component of switch drive signal, conceptually derived or conceptually understood in this manner. Okay, and the formal definition, we are assigning number one here when this QT is 1, when this voltage high, and when this voltage is low, we assign 0. Okay, this is called the switching function. Then you can perform the mathematical operation on this. Then dt is defined as this. This is the integration for one switching period. Q, we need dummy diode tau and d tau. Okay, and we integrate just one switching period and divide by this one switching period. Then duty ratio is 0.5. This value will be 0.5. Okay. Then we are taking the moving average, sliding this slope, TS slope in time, sliding this in time. Then we generate the continuous waveform. Then we have some waveforms very similar to this. Okay. There is just some approximation to equate this and this one, but we are assuming that approximation is valid. Okay, so this is the moving average, local moving average of switching function assigned to this switch drive signal. So conceptually, this one is very similar. This one is extremely easy to understand. This is some mathematical, but conceptually it is also easy to understand. Okay, you are not calculating this. You don't need to calculate this. Just understand this. Okay, all right. And this is that called the cycle by cycle duty ratio dk, and this is this AC plus this is continuous duty ratio dt. This is the steady state duty ratio. This is the small signal continuous duty ratio. Okay, so based on this concept, then we develop this small signal model of this previous open loop controlled PWM converter. So we are trying to evaluate transfer function from here to there. So we assume this one is 0, showed it, and another disturbance coming from the output is 0. So that is opened. Okay. This is possible because we are considering this as a linear time invariant system. Then superposition hold. Then for that, we only need to consider this sinusoidal waveform, and this is shorted, and this current source is opened. Okay. So and we have continuous sinusoidal wave here. Then you can define this small signal model of power stage is linear time invariant circuit model. Okay, very easy to understand and analyze. And this is the constant. So this is the regular. Then you can easily evaluate the transfer function from here to there using extremely simple circuit analysis technique. That is the transfer function GVCS, and maybe this one. Okay, probably this one. For some case, okay, maybe we need another one. Okay, for the converter, there's only 0, regular 0. called the ESR0 for the boost and the buck boost converter. We have this term with the negative sign. There is the right half plane 0. That is called omega RHP. It's right half plane 0. And the denominator is standard second order system. And with this, you can draw the Baudel plot of this one. There is the frequency response of this your converter at given point under assumption you are not moving much away from the given point. Then this is valid, very close approximation. Okay. For that, we need the small signal model of power stage and the PWM block. Okay. We'll discuss this first and second one. Okay. We are not discussing, we are just reviewing the previous knowledge, but I selected to follow this simple approach. Okay. This is the very intuitional and the easy approach to understand everything. So you have this. Okay. So this actual waveforms, this is the PWM waveforms, and this is a pulse width modulate PWM gate drive signal, and this is the VQT, and this is the continuous duty ratio we went through in the previous slide. Okay. Then think about this. So we have a lamp. Okay. There's a fixed lamp, and the input to the lamp is this one. So we are comparing with this lamp and this signal. So this signal has a DC component and AC component, and AC component is sufficiently smaller than DC component. Then we have a small variation here. And for DC, we have steady state duty ratio T. And for this excursion, we have this. And for this negative excursion, we have this. And this is defined as D hat, which is small signal continuous duty ratio times DTS. Okay. The length of this is not D hat times TS. Right? It's so obvious. Okay. And this is the DT continuous duty ratio, which is D times I think get rid of this. Okay. So dt, okay. This is the function, and I'm talking about this, the length. These two different things. Okay. I'm not sure. Okay. So this can be removed. Okay. Okay. So this is input and this is output, but somehow we want to have the relationship between this V con hat and the D hat. Okay. Then just to write down relationship between this and this. And this variation is DTS. Okay, so consider this is the input. Actual input is this one, but consider this is the input prime. Okay, then this times the slope is this one. Okay, so this is this one variation in this time axis times this is the slope of lamp that generate this AC signal. So this is AC and the constant AC signal. Then ratio between V con hat and the D hat is called modulator gain FM is 1 minus VM. Okay, this is well known in many ways, maybe 10 different ways of explaining this. This is one way of them. One of them. All right. So if VM is 1, then FM becomes 1. Okay, so it's better to use 1. This VM. Okay, then you don't have to worry about the modulator gain, which is 1. Okay, so for the small signal block, we are using this notation. This is the input to this PWM block, and output is this one, and the input to output relationship gain of this PWM block or modulator gain, FM is 1 over VM. This is input, this is output, and this is gain. Okay? So we know the modulator gain, which is just constant. All right. Then next one is we should discuss the small signal model of PWM power stage. Okay. This is the 3 different converter: buck converter, boost converter, and buck boost converter. and it has the common component, this and this and this, okay? You can combine with this, okay? Or you can just use this. Maybe this is better to combine this capacitor. No, this inductor will be better. So maybe we extend like this. This is called the three-terminal device. And this is general layout. You rotate this, and with this connection like this, it becomes a buck converter. And if you rotate 120 degree, it becomes a boost converter. Another rotation is a buck boost converter. Another rotation come back to the buck converter. Okay, just rotating this. Right. The reason showing this is these are only time varying nonlinear component in the circuit. Right. This is the remaining part is this is the linear, this is the linear, this is the linear, but it's rotating, so can be considered as a nonlinear time varying element. Okay, and this the linear part, maybe you add another stage of something, another strange circuit that is linear, that remain the same. Okay, during the process of averaging and linearization, it remains the same. Okay, then what we need to worry about is only this one. If you develop this small signal model of this part, then you just replace the then model with the pin-to-pin change in the node. Then you will come up with three different small signal model of three different PWM converter power stage. Okay, that is the concept of this. In the past, they used the state-to-state averaging something. Okay, that is not necessary here. State averaging circuit is very mathematical and very general, but we don't need this, okay? Because we are using only this SPT switch a lot, okay? That is the kind of overkill, okay? Right? So from this, we take out this and we develop small signal model of this. This topic is covered in lecture topic 8 with 11 lectures. For the complete details about this, you need to watch these 11 videos, okay? If not, you take this as true, okay? You take this granted, okay, then this is fine. Then small signal model of this is this, right? So it has this, it contains the DC information because this is the steady state UD ratio. This is the DC voltage across this A and P terminal. This is the DC current leaving from this common terminal. This is called A, active terminal, passive terminal, common terminal, inductor terminal here. Okay, same thing, right? Then you just replace this, take out this, go through this procedure, and put it back to here, and you rotate 3 times. Then you will come up with the small signal power stage model of buck converter, boost converter, and buck boost converter. Okay, we will be using this because flyback converter is actually buck boost converter with transformer isolation. So we will be using this. So this is important, okay? Right, okay? This is summary, okay? We skip the details about the small signal model derivation. That will take the 10 hours like that, okay? Complete details about that. That is posted in EE classroom and the YouTube site. Okay, if you want, you can go there, right? So now we assume we have the small signal model for the buck converter. This is connected here. This is connected. Then it becomes buck converter. Okay. For the buck converter example, you can derive this for this buck converter. You derive transfer function from here to there. Extremely easy. Okay. Because D is source is here, and source is here. There's a current source, okay? But this input voltage showed it because input, you are not considering input. Input is dead, so it's showed it. Then current will self-circulate, does not go into this direction, so it's nothing. Then this voltage is appearing here, and you have duty ratio. You have this 1 to D, they cancel, and this VAP times the VAP is VS input voltage for the case of a converter. Then that voltage is just divided by this two impedances, this one and this one, extremely easy. So you generate this and multiply this, then that becomes control to output transfer function, this one, but which is actually multiplication of this transfer function and this transfer function. So it looks like this, okay? So this one is Fn times GVDS. GVDS is duty ratio to output transfer function. Very simple in this circuit diagram, but very difficult in measuring or simulating using the empirical method, right? So having this model is very good because you can easily evaluate this because this is a linear circuit. Anyway, you get this result. Then if you divide this one by this, you will have this one. So maybe you can calculate this or experimentally measure this, or you can get from the time domain simulation. Then convert them into Baudot plot. That is the frequency response plot shown here. So these are three different cases, small signal analysis using this, and the measurement using some equipment, and the computational method using time domain simulation. Okay, this is the same as experimental measurement. Okay, is the substitute for this experimental measurement. There is no modeling or no analysis here, just doing simulation. Okay, so they are very similar, and there are some minor difference here at high frequencies. There is the numerical garbage coming from the integration routine used in this PC or other software. Okay, at high frequencies, signal level is very low. Okay, and so there is just some noise is amplified and generates some garbage. Right. So with this, we revisit this one. Okay. So from the previous knowledge, so it looks very natural. Okay. So we can evaluate this using the empirical approach or using the small signal model of power stage and the PWM block. Okay, empirical method. One is measurement, the other one is simulation. Okay. And frequency response of that is this one. When you are evaluating, assume this is 0, this is showed it, I/O is 0, this is opened, this is possible, this is a linear time invariant circuit. Okay, there is. And I call it practical model. That means this RL is here and RC is here. There are two parasitic resistance. Okay, that is practical model. Sometimes you ignore this, showed it here, then that becomes maybe simplified model. That is okay. Okay, if you ignore this, that is ideal model. Okay, but this one is very extremely important. RC is creating a 0 here. Okay, so this one, the 0 created by this and this combination will show up in all the transfer functions. Okay, but this one can be ignored. This one only occurs the transfer function from here, this load current to our voltage. So sometimes that can be ignored. Okay, so let's take the buck converter example. This is the circuit diagram of a buck converter, and this is a practical small signal model because I include this and I include this. Okay. For example, duty ratio to output transfer function. So duty ratio is here. This is here. Okay, and this is showed it. So this current is just circulating within this loop. So it does not go into the other way around. So it is nothing. It's just waste. And that this voltage is appearing here. Then they cancel. And Vs is coming here. And that voltage is DC. Voltage is divided by this and this, which is shown here. And this is a voltage division of this one, this one, this one, this one, plus this one. Okay, it's just this. Okay, this is Ohm's law. Okay, don't call it analysis. Ohm's law. Okay, then simply using some simplification, if RL is much smaller than this is reduced to this, and we have 1, 0. So this is the exact one, and this Q. And this omega naught is double pole frequency, and this quality factor of this one is this complicated one. But if you ignore this one, then it simplifies to this, Okay, so this is the asymptotic plot of this transfer function, control to output transfer function. And if you have asymptotic plot, you include this peaking here, peaking of 20 log Q. And you smoothly connect them like this, then it's very similar to the actual simulation using some computer or some stupid things. So very similar to this. Okay, but you don't have to just sketch this. There is more than enough. Okay. Accuracy of this response, right? So we derived this and we assumed this is correct, and we generate a transfer function based on this, and we plot them all together. We overplot small signal based this analytical prediction and experimental measurement and computational method using time domain simulation. There is no analysis, just the simulation. Okay, same in the similar manner to the experimental measurement. So they are the same, practically the same. Okay, don't ask the reason why this some discrepancy. I cannot explain it. It's garbage. Okay, numerical garbage. Just ignore that. That is occurring in the hardware measurement, also occurring this computational simulation. Numerical noise is also noise. So this is the exact expression for this power transfer function. So you don't have to do this. Just take this granted. That is fine. So this is exact expression, and you won't have a chance to use this. If you use this, you are doing something unnecessary. Okay? You are assuming you are dumb. Okay? Just ignore that. All right? This one. And the simplification, I said this is, okay, let me explain this. This omega ESR is coming from this structure. Okay, this is the exact one, right? So you have this series combination of the resistor and the C. Always it is coming up. This is 0. This is called ESR, equivalent series resistance of capacitor. So this is called ESR 0. This exact expression, and this low frequency is this is not exact. Okay, this is the exact. Yeah, this is the exact. I'm sorry. This is the exact expression, and this is the exact one, right? But simplification. I'm using term exact model, which is 2 parasitic resistance on the 2 reactive component. This is the exact. And sometimes I drop this, but still keeping this. This is simplified. Sometimes I use this for the purely theoretical discussions is ideal component. Okay. So this is the exact expression, if this condition is valid, this is always valid, okay, then this is the exact one, and omega naught, use this, and the quality factor use this, and this, the low free scale is, this is their approximation, and this one is exact. When you assume this RA is 0, still RC is small, but there is RC, then this is the same exact expression. This is a 0 and this is a 0. Okay? Because RA is 0, then this omega ESR is still there. Okay? So this is important. If you ignore this, you are kicking out one slope increase, all right, which is substantial in your analysis and the prediction. Okay, for the frequency response, 0 is very important. 4 is important. Okay, when RC approach to 0, then omega ESR go to higher frequency and arrive infinity. Right? So you can, so it goes out to infinity. When RL goes to 0, omega 0 approach to 0 frequency. Meaning of that is you have 0. At 0 frequency, that is the initial slope is this one. Initial slope is this one. Okay? Suppose this is the something, you have 0 at the origin, 0 at the 0 frequency. It starts with differentiation. It starts with +1 slope like this. Okay? So 0 appears at omega g appears at 0 frequency, or this one, they cancel. Okay? You can easily deduce this, and it reduced to the S. Okay? This only S, which is differentiation, remains the true. It survives. Okay? So you start from S, then you have this differentiation in the beginning. Okay? So this is the asymptotic diagram of 3 transfer functions: Dewey ratio to output, and the input voltage to out voltage, and this is the load current to out voltage. Okay, so it starts from the this one 20 log RL, which is ESR of inductor. If ESR is 0, then this curve starts from this +1 slope. Okay. So it starts with this differentiation, +1 slope, and go to the -1 slope at this double pole frequency. Okay, so this is the case when this RL is 0. Okay, and implication of this. So from these steps, we derive the small signal model of power stage, okay, and we derive the small signal model of modulator block PWM gain, and later on we will derive the small signal model of compensation circuit, which is extremely easy. That circuit is already linear. You know how to derive the gain of inverting amplifier. So we have everything. All right. Then you can apply all the techniques available for the linear invariant system, transfer functions and Laplace transformation, and root locus, Nyquist, whatever. Okay? So you move the linear, nonlinear time varying PWM converter in the region, in the regime of linear systems. Then you massage it with all the techniques developed for the linear time invariant system. That is the object of this small signal modeling. Okay? Many students, they ask, what is the small signal model? Explain it to me. This is my explanation. It takes time. Okay? So that is not easy. Okay? It does not mean something is small. Not simple like that. Right? So it's related with our attempt to use the existing technique to analyze and design the originally not intended to be applied. Okay? And one simple, so there are many implications, right? Let me show you just very simple implication. Okay? If I show this, the student, they think this is the purpose of deriving the small signal model. That's not the case at all. Okay? I'm showing this just one simple example. Right? There are a huge application of this. Right? This is one simple example. This is the input to output transfer function of the buck converter. Okay? Input to output transfer function of buck converter. And this is one thing. And another thing is you generate some waveforms. Okay? This is the converter used duty ratio D was 1/4. That number is used to derive this transfer function, frequency response of transfer function in exact sense. Okay, then you excite this signal. This is the open loop buck converter, ideal buck converter. Okay, so QT, duty ratio of QT is this one, 1/4, and this input voltage is 16 plus AC sinusoidal wave, and the sinusoidal wave is frequency is 2 kHz. So you take a look at this curve. This is the input to output transfer function. Okay, so at 2 kHz you are watching this. Then phase delay is minus 130 degree. Okay, approximately, and the magnitude is minus 20 dB. Implication of this is if you apply this plus this one, then magnitude of this 2 kHz sinusoid will be attenuate to 1/10, 20 dB, and the phase will be delayed 130 degree. That is the prediction of this. Okay, check that out. So for this simulation, I did a simulation because this is the 16 and this AC component. Magnitude of this is 0.5. This is 0.5, and the frequency was 2 kHz. Then our prediction is this one. Output is this one. This is DC. This is converter, not a linear circuit. So our voltage is generated from the principle of buck converter, and this is attenuation. Predict here 0.1 times this one is 0.01. Okay, and this is the ripple component. So ripple component is something else. But if you want, you can easily calculate this simply. Okay, very simply, just applying the Ohm's law. Okay, every circuit analysis here is just Ohm's law. I call it Ohm's law always from now on. Okay, use Ohm's law, then ripple component can be accounted here. All right, and then this output is this one. This is the prediction from this small signal model, and the result of the time domain simulation. You take this mid envelope. Okay, this magnitude is this one, and if you take the close look at this point, and you have this degree delay should be okay. This is the implication, or one simple implication of this frequency response. There are many other more important implications you will be learning. Another one, very similar one. Okay, this is the duty ratio to output transfer function. So I'm interested in this frequency, which is 1, 2, 3, 4, 5 kHz. Then this is the 0 dB line. So gain is just the unity. So input in is input out with the same amplitude. Okay, and this is the fixed. Previously D was fixed. Okay, only one thing is changing because this superposition. So if you change two things together, you got mixed up. You cannot distinguish between them. Okay, just one perturbation at a time. So now this voltage is fixed and the duty ratio is changed. Okay, This is a duty ratio changed. The only way of achieving this is you modulate the switch drive signal with some software, okay, with some simple calculator. So if you take a close look at here, modulator here is large, here is small, okay, and the change of modulator is this sinusoidal fashion, and this average value is 0.25, and this amplitude is, this one is 0.05, okay. Then based on this, at this frequency, okay, then this is 0. 0 means this magnitude remains the same. So take a look at this mid curve through this ripple component. Then this magnitude is 0.05, and you have phase delay here. So that phase delay should be same as this one. I don't know which number, but some number, arbitrary number, not arbitrarily, maybe this one. 135-degree phase margin, okay? And so the same, and you should consider separately, because this is a converter, okay? This is not a linear circuit, this converter, you should consider this always, okay? All right, so this is a summary of small signal modeling and the frequency response of PWM converter. So even though we didn't cover the details about the deriving small signal of this component, actually this is called the PWM switch. This is called the PWM switch model. Okay, if you accept this, if you take this one granted, then you don't have any problem. Okay, then you can move forward this the dynamic analysis and compensation design of our converter. So next lecture we'll cover that. Right? So that will be very easy. And the current mode control and dynamic analysis and compensation design, performance prediction, evaluation, and optimization is coming later. Okay? All right. Okay. We'll stop here today. Okay? See you next. No, not this coming Thursday. Okay? All right. Thank you.